After Langevin theory of paramagnetism, which is a classical theory, we're going to continue with the quantum theory of paramagnetism. First, we're going to demonstrate this for a single electron spin. So for a single electron spin, we have the spin quantum number S is equal to J. So J is equal to capital S is equal to 1/2, and this gives us two possibilities for m sub s, which is plus or minus 1/2. The corresponding value of the lambda factor G is going to be 2. Therefore, we can have for the magnetic moment of the spin m minus G Bohr magneton m sub s, which is going to be plus or minus a Bohr magneton. Now, if the magnetic moment is plus Bohr magneton, so I'm going to make a table here. So let's first take a look at the possible values of m. M can take values plus Bohr magneton or minus Bohr magneton, and the corresponding value of the energy will be when the magnetic field H is applied in the up direction, so that when the magnetic moment is plus Bohr magneton, they're going to be parallel to each other. The corresponding energy will be, using SI units, minus mu0 mu b h, and when it is minus Bohr magneton, it will be plus mu0 mu b Bohr magneton times h. So this will be the energy E of the system, and then corresponding to this I have to find the Boltzmann factor. So I will have e to the minus e over kBt, the Boltzmann factor. This is going to be equal to e to the plus mu0 mu bh over kBt, and for this scenario I will have e to the minus mu0 mu bh over kBt. Okay, the total magnetic moment m will be the number density of atoms multiplied by magnetic moment per atom, m. So this is going to be equal to for an m value, which is, so we can consider the average value of m bar will be equal to the value of m multiplied by its corresponding probability. So it's going to be sum over I from 1 to 2, the possible values of I multiplied by their corresponding probabilities. Okay, so Pi is probability of m equals m sub I. So if you calculate this, you will find m bar is equal to, so we have the first scenario, m is equal to mu b, the corresponding Boltzmann factor e to the plus mu0 mu b h over kBt, and then the second possibility is minus mu b with the corresponding probability minus mu0 mu bh over kBt, Boltzmann factor, and this has to be divided by the partition function e to the plus mu0 mu bh over kBt plus e to the minus mu0 mu bh over kBt. So we can say that the probability for ith value is proportional to e to the minus e over kbt. This is given by the canonical distribution for this system. So you can see that the average value of the magnetic moment of this spin will be equal to a Bohr magneton mu b times, if I call this factor mu 0 mu h over kbt alpha, mu 0 mu b h over kbt, then I will have here e to the alpha minus e to the minus alpha divided by e to the alpha plus e to the minus alpha, and that is, from the top I can see that e to the alpha minus e to the minus alpha divided by 2, that would be sine hyperbolic. For the bottom I would have e to the alpha plus minus e to the minus alpha over 2, that would be cosine hyperbolic. So this is mu b times tangent hyperbolic alpha, where alpha is here. So it would be mu b times tangent hyperbolic mu 0 mu b h over kbt, and therefore for the total moment I would find the total moment equals to m, that is the number density times the average value of the magnetic moment. So this would be equal to nv times the Bohr magneton mu b tangent hyperbolic mu 0 mu b h over kbt using SI units, Boltzmann constant times temperature. Now we know that this alpha value, alpha, is much less than 1 typically, because we have quite small numbers in the numerator. Mu 0 is 4 pi 10 to minus 7. Mu b, Bohr magneton, is also a very small number. So I have alpha typically much less than 1. So basically I can see that an approximate value for m would be nvm. Now if I expand this e to the alpha, I would get so e to the alpha around alpha equals 0 is 1 plus alpha plus alpha squared over 2 factorial, etc. So for this one I would get 1 plus alpha squared over 2. And then for e to the minus alpha I would get minus, so let me turn this into a square parentheses. Then I would get for e to the minus alpha 1 minus alpha plus alpha squared over 2. The first 3 terms in the Taylor series expansion. And at the bottom I would have 1 plus alpha squared over 2 plus 1 minus alpha plus alpha squared over 2. So this would give me, for the total magnetic moment m, number density times, this is a Bohr magneton, so for small alpha this would be number density Bohr magneton. As you can see, I would get here, when I operate this parentheses, 1 plus alpha squared over 2 minus 1 plus alpha minus alpha squared over 2, and at the bottom I would get the plus alpha and minus alpha cancelling, and I would obtain 2 plus alpha squared. Okay, and now on top I have plus alpha squared over 2 and minus alpha squared over 2 cancelling, and plus and minus 1 cancelling, so I obtain 2 alpha. So this would be number density Bohr magneton times 2 alpha divided by 2 plus alpha square, but now alpha is much less than 1, then alpha square is much less than 2. So I can basically write for the total magnetic moment number density Bohr magneton multiplied with 2 alpha divided by 2, so these will cancel. So I will find that the total magnetic moment is number density Bohr magneton times alpha, which is mu 0 mu bh over kBt. So if I rewrite this, a typical value for the total magnetic moment is number density Nv mu b squared mu 0 h divided by kBt, so that the susceptibility, which is m divided by h, would become Nv. Now mu b squared, so mu b is the value of m basically, so it's the value of m square, magnetic moment of the spin squared, multiplied with mu 0 divided by kBt. So I have obtained the susceptibility of a single electron spin using quantization taking quantization into account, so it's quantum statistics. Okay, so once again I see that the Curie law is here. It is basically Nv m square mu 0 over kBt, so 1 over t dependence is still present using the quantum theory. Now if the atom has, so we're going to generalize this to 2j plus 1 energy levels, so not a single spin. So if we generalize it, if the atom has more than one electron, then we should consider mj values between minus j and plus j and 2j plus 1 energy levels. So in that case, this result is modified, and I'm going to write this without proof, but I'm going to check if it's valid in some limits. The total magnetic moment per volume, magnetization, will be number density Nb G J Bohr magneton, which is our general quantum mechanical result for magnetic moment per atom, times the Brillouin function, which is as a function of J, multiplied, as a function of the same alpha value, G J Bohr magneton mu 0 h over kBt. So this is the Brillouin function is a function of this alpha. So we're going to use this and check it in some limits where we have Bj of x is the Brillouin function. So instead of Langevin function, we have a Brillouin function, and the Brillouin function is given by Bj of x is equal to 2j plus 1 over 2j cotangent hyperbolic two j plus 1 x over 2j minus 1 over 2j cotangent hyperbolic x divided by 2j. So this is our Brillouin function. Now if we use a Taylor series expansion of this Brillouin function, then we can find a susceptibility. So if we substitute for x, where x is equal to gj Bohr magneton mu 0 h over kBt. So I want to check some limits. Now if I look at what happens when this x is small, which is the general case, so x is much less than 1, what is going to happen? So if x is much less than 1, then I can use the expansion of a cotangent hyperbolic function that is the that was basically shown in the Langevin theory. So if x is much less than 1, cotangent hyperbolic of 2j plus 1 x divided by 2j is basically, according to our Langevin theory expansion, remember we have cotangent hyperbolic y is for small y 1 over y plus y over 3. So we're going to use the same result here. So it's going to be 1 over 2j plus 1 x over 2j. So it will be 2j over 2j plus 1 x plus 2j plus 1 x over 6j. And for cotangent hyperbolic x over 2j, I'm going to write 2j over x plus 3 plus x over 6j. Okay, so with this we can find what happens to the Brillouin function. Brillouin function is a function of x for x much less than 1 is going to be equal to 2j plus 1 over 2j, 2j plus 1 divided by 2j multiplied by the cotangent hyperbolic function x over 2j plus 1 x over 2j. So it's going to be 2j over 2j plus 1 times x, and then plus we will have the second term 2j plus 1 x over 6j. That is the first term, and then minus 1 over 2j and for cotangent hyperbolic x over 2j we will have 2j over x plus x over 6j. So if you do this multiplication, you can see that the first term will be 1 over x. The second term will be 2j plus 1 squared x divided by 12j squared. And then we will have minus 1 over x. And then we will have minus x over 12j squared. So plus 1 over x and minus 1 over x will cancel. And here we will obtain in x over 12j squared parentheses 2j plus 1 squared minus 1. So this will be equal to x over 12j squared 4j squared plus 4j, and then it will be plus 1 and minus 1, so they will cancel. So this is going to give me, the brilliant function will turn into x over 3j. The 4 will cancel, 4 will turn 12 into 3, and one of the j's will disappear. So I will have x over 3j multiplied with j plus 1. So if I go back to my magnetization, the magnetization then will become NVG Bohr magneton times j. So I will have x times j plus 1 divided by 3j. So this j will disappear. And then for x, I'm going to substitute gj mu 0 mu b h over kbt. So I will have and v g mu b times x, which is g j mu b h over kbt, that is x, and then I will have j plus 1 over 3, so this will turn into nv g square mu b square j plus 1 h and I also had a mu 0 in x, so there's a mu 0 here, so there is a mu 0, so it's going to be times mu 0 divided by 3 kBt. So this will basically turn into a susceptibility in SI units, that is the number density NV g square jj plus 1 Bohr magneton square mu 0 divided by 3 kBt. And you can notice that this can be written in the form NV m effective square mu 0 over 3 kBt, where m effective is g square root j plus 1 Bohr magneton. So it's actually the magnitude of the magnetic moment. So we have found the susceptibility in SI units in this form, and it also has 1 over t dependence. as we have seen in the Langevin theory. Now, another thing I would like to check is what happens if I'm in the classical limit. If in the classical limit I have J is infinite, so I have a very large quantum number, that means I'm in the classical limit. What happens to the Brillouin function? Well, you can see that the Brillouin function, if I rewrite it here, so let's copy this. Here. So in this limit, you can see that I will have, when j is infinite, it will be much greater than 1. So I will have 2j over 2j. So this is going to turn into 1. And then 2j plus 1 over 2j, again, this is going to turn into 1. And then I will have this term, x over 2j, will be much less than 1, so I can use the Taylor series expansion of cotangent hyperbolic in order to avoid the 0 here. So this is going to be equal to, approximately equal to, cotangent hyperbolic x, and then I have here minus 1 over 2j. The first term in the cotangent hyperbolic expansion, cotangent hyperbolic of alpha, for small alpha was 1 over alpha, remember. So if I use the first term, it becomes 2j over x. So these will disappear, and basically I obtain cotangent hyperbolic x minus 1 over x. And what is this? This is the Langevin function. So the Brillouin function turns into Langevin function in the limit j is very large. And one other limit I would like to check is what happens if I substitute for j 1 over 2. If j is equal to 1 over 2, and so that I have a single electron spin. I also have a result for this one. For the single electron spin, what happens to the Brillouin function? So Brillouin function for j equals 1 over 2x. So this is going to become, when I substitute j is equal to 1 over 2 times 1 over 2 is 1, 1 plus 1 over 2 times 1 over 2, 1. So I will have 2 divided by 1, 2 cotangent hyperbolic 2x, and 1 over 2j will become 1 minus cotangent hyperbolic x. So basically I would like to show that this is tangent hyperbolic. So this is going to be 2 e to the 2x plus e to the minus 2x cosine hyperbolic divided by sine hyperbolic e to the 2x minus e to the minus 2x, and then I have minus e to the x plus e to the minus x divided by e to the x minus e to the minus x, and I see that this is in the form e to the x plus e to the minus x multiplied with e to the x minus e to the minus x. It is a squared minus b squared, that is a minus b times a plus b. So if I multiply the right hand side with e to the x plus e to the minus x, I can add these up. So this is going to be 2 e to the 2x plus 2 e to the minus 2x, and then I have minus e to the x plus e to the minus x parentheses squared divided by e to the 2x minus e to the minus 2x. So I multiplied the right hand side with e to the x plus e to the minus x. So this is going to give me, for the brilliant function in this limit, brilliant function in 1/2, j is equal to 1/2, is 2e to the 2x plus 2e to the minus 2x minus e to the x square, e to the 2x, plus 2 will become minus 2, plus e to the minus 2x will become minus e to the minus 2x, and this divided by e to the 2x minus e to the minus 2x, and this is going to be, one of the e to the 2x's will disappear, e to the 2x and one of the e to the minus 2x's will disappear, e to the minus 2x minus 2 divided by e to the 2x minus e to the minus 2x, and you can realize that the top is basically square of e to the x minus e to the minus x squared. So this is e to the x minus e to the minus x and e to the x plus e to the minus x, and so this will get rid of this one, and you will obtain e to the x minus e to the minus x divided by e to the x plus e to the minus x. So what did I find? Brilliant function for j is equal to 1/2 is equal to tangent hyperbolic x. So in agreement with the single spin result. Okay, so basically this completes our discussion of the brilliant function, and finally I would like to take a look at the magnetic moment of potassium, chromium, aluminum as a function of h over t as an example. You can see j is equal to infinite, the Langevin limit here. The quantum limit has j is equal to 3 over 2, g is equal to 2, and for this one we see that the data, the actual data, completely agrees with the brilliant function where j is equal to 3 over 2. So we can see that the classical result is not too far off, but especially for high magnetic fields and low temperatures, we see that the difference between classical and quantum result is increasing. Okay. All right, so we have talked about quantum theory of paramagnetism. We started out with a single spin where j is equal to s is equal to 1/2. The spin quantum number can be plus or minus 1/2, m sub s can be plus or minus 1/2. Lambda factor is 2 if we have spin only. The corresponding magnetic moment is minus g Bohr magneton m sub s. So it is either plus Bohr magneton or minus Bohr magneton. If you have plus Bohr magneton, the corresponding energy is minus mu 0 mu b h if h is up, and the corresponding Boltzmann factor is e to the plus mu 0 mu b h over kBt, because it's e to the minus e over kBt. And similarly for minus b. And the magnetization will be number density times the average value of the magnetic moment. Average value of the magnetic moment is calculated by multiplying the individual values, possible values of magnetic moment with their corresponding probabilities and adding up over all possibilities. So that's what I did here. I have written the canonical distribution of the magnetic moments, and I basically obtained mu b times tangent hyperbolic mu 0 mu b h over kBt. And because this mu 0 mu b h over kBt is a rather small number, typically mu b is small, mu 0 is 4 pi 10 to minus 7, it's small. So this usually turns out to be much less than 1. And so we can use the exponential expansion around e to the alpha around alpha equals 0. And with this approximation, we can obtain the susceptibility to be number density, number of atoms per volume, m square magnetic moment per atom, which is the single electron spin, multiplied by mu 0 over kBt. So that is in the form of C over T, so this is obeying Curie's law. So if the atom has more than one electron, then this is replaced by Nv times Gj mu b, the magnetic moment per atom, times brilliant function Gj mu b mu 0 h over kBt, where Bj of x is called the brilliant function, and it has this form. And when x is much less than 1, the brilliant function we have shown turns into a simple expression, but we have basically used cotangent hyperbolic expansion. So we remembered that cotangent hyperbolic x for x around 0 was given by 1 over x plus x over 3 plus higher order terms. So that's what we used, and we have obtained the susceptibility value, where we found that it can be written in the form number density m squared mu 0 over 3 kt, but m squared is the effective magnetic moment, which is g square root jj plus 1 mu b, which is actually the magnitude of the magnetic moment. So here it was actually mu b, just mu b, because, well, actually it's the same thing, because j was equal to 1/2. So in the classical limit, we checked what happens when j goes to infinity. We found that we recover the Langevin function in this limit, and we also checked for what happens when j is equal to 1/2. J is equal to 1/2 gives us the tangent hyperbolic result, in agreement with the single spin calculation we did at the beginning.